I'll edit it to 0 now. Just kidding.
Right on. So hey, I haven't seen you guys in a really long time. It's awesome to see you. Wolfram, remember the trip to Hawaii?
Yeah.
Come on, man.
Okay.
So now you're at Facebook.
Yes, nice seeing you, Charles, again. And I'm here with Jan Gray. And I haven't seen Jan for at least a half year. We'll see each other a little bit more often.
And so there was the 20th anniversary. What is it, the 25th anniversary now?
Just came the 25th.
Dude, I saw
right.
Rico Mariani had hair.
Yeah.
I saw the video on
some of us
YouTube.
had hair.
And so did
Yes.
you. So congratulations on that, by the way.
Thank you.
So I guess, what have you guys, what have you been up to since, for the past few years?
Cool. Yeah, so approximately 2 years ago, I left Microsoft. I had a fun time at Microsoft. I did some retirement, and after finishing all home improvement, I got bored and said, I need a new challenge. So I thought I'll pick a little bit younger company and join Facebook.
Cool.
And since then, I'm actually a programming language guy, but I thought, well, I have to learn how things are done, and I started in the data center, and I slowly moved up the stack, and I'm back to programming languages. So
Awesome.
cool. But I think as Jan has probably an equally interesting journey behind him. So what did you do?
I've been working on FPGA multiprocessors. You saw the Catapult stuff, which was way cool. I worked a little bit on Catapult at the very beginning of that project.
Nice.
I'm proud and amazed at what that team has done. It's perhaps the largest installation of FPGAs.
And we're talking about in Microsoft Azure.
Microsoft Catapult,
Yeah.
Catapult V2, the Smart NIC, the very cool Brainwave, real-time AI at scale. Really cool stuff. My work has been in building soft processors with FPGAs and FPGA efficient networks on chips. So first I've been recently implementing the RISC-V instruction set architecture. You may have heard of RISC-V. It's an open instruction set specification. There's about 20 different independent implementations of RISC-V. I build some of the smallest implementations and most area and energy efficient implementations of RISC-V for FPGAs. And then the FPGAs these days are so enormously large that I could put 1,000 to 2,000 cores on one chip. They're wimpy cores. They're single issue scalar processors that run at 250 to 500 megahertz, but in aggregate, that's a lot of compute. And I'm building out a parallel computer design for that. And until recently, it was a bit hopeless to get that into industry. You had to be a large company or be able to go and get boards built and support people. But we're starting to see the advent of FPGAs in the cloud. So back in December of 2016, Amazon brought out a new machine instance type called F1. F1 combines a Xeon with 1 or 8 large Xilinx FPGAs. So on that I could put 1 to 8,000 RISC processors on one machine instance that's coupled through PCI Express back to the host that's running Linux. I'm currently working on an OpenCL stack for that. It's one thing to, you can compile with GCC code that targets RISC-V and run it on all these cores, but and then use message passing amongst them. But that's a programming model that only I can successfully learn and use. And I'm going to try and tie my cart to the OpenCL horse, or whatever the right metaphor is. OpenCL is becoming a popular way to express flat data parallel workloads, and it not only is it being used for GPUs, but we're starting to see it be used for FPGAs as well.
Interesting.
So can you say a little bit about the efficiency between the GPUs and the FPGA, and also maybe about the huge power that FPGA was used in the past, and what has happened there? Is it substance? Are we
right? So
on par?
Very good. So field programmable gate arrays are programmable logic gates and programmable interconnect. So if you can conceive of a digital logic circuit, you can go and build it in an FPGA. Because the wires are all programmable rather than drawn copper wires, there's a 100 to 1 loss of density in the wiring and the gates that you get. But when you have embedded memories, embedded multipliers, and so on, those are just as efficient as full custom. So where people see an acceleration with building a computer in FPGAs, it's when they take some workload that they run all day long and they figure out what are the memory access patterns and they go and build a hardware design that's perfectly elaborated for that problem. So the Catapult Bing search ranking algorithms, that was the first target of Catapult. The team went and mapped different parts of that document ranking data path, a document ranking algorithm into custom data path. And you're not running at several gigahertz like an Intel chip, but you can make several hundred or several thousand memory accesses per clock cycle. So you make it up in enormous spatial parallelism. Now, the really interesting topic in both GPUs and FPGAs these days is running deep convolutional neural network accelerators. And although GPUs have a huge lead in training for the inference side, FPGAs are catching up with GPUs in terms of efficiency. Part of it is that over the last 7 years, these deep CNNs have gone from doing 32-bit float precision weights and activations to 16-bit half float to, oh, we can go to 8-bit int and have most of the accuracy, 4-bit int, 2-bit int. They're actually starting to see so-called binary and ternary neural networks where there's 1 or 2 bits of weight in each of those weights on those things. And that's where FPGAs, which are bit-oriented, can beat GPUs both in absolute perf and in energy efficiency.
Okay.
And also where FPGAs are good is when the machine learning algorithms are rapidly evolving, where it's not just dot products of floating point vectors, but as we're starting to see other encodings of problems, or other things that are not even CNNs that you can map into FPGAs. So that's, there's this agility trade-off that FPGAs have versus the full custom advantage that GPUs have.
Yeah. So let me ask maybe one question about the agility. So suppose we are deploying code constantly, and then it has to go through all machines. If you have whatever new features, new experiments, new models, how does that work with FPGAs? In some sense, how quickly can you, in some sense, get a new model deployed on all the different cards?
It's a challenge, right? So if you're designing your FPGA custom computing circuit in low-level hardware description language, Verilog or VHDL, then the software guy comes in and he says, I've got a great new algorithm, I've got a great new data structure, and you go, oh no, I've got to rewrite 10,000 lines of the lowest level register transfer language. Come back in 3 months. Or please don't do that, right? So that's a challenge. Typically what has worked well, I've observed that the Catapult team has made this work well, is to build an intermediate overlay layer where they have an abstract computer that's optimized for a particular problem, and then you can load new coefficients, new problem shapes and sizes onto that. And then it's as quick to do a turn as if you changed a line of code in your GPU code and recompiled.
So we built more or less like a configuration, right? They're changing the configuration of the
load new tables, load a new context. And so, in fact, the stuff that I'm doing where you've got this big array of soft processors, I think will compete well with the current tools that Intel and Xilinx are putting forward for OpenCL, where you change a line of code and they synthesize a new data path that's optimized to that kernel.
I see.
And then it goes through a 5-hour place and route, right?
I see,
They're very frustrating for a developer who's used to 1 second turnaround. Whereas if you're targeting an overlay, you change the code and you just push a new binary into the accelerator array.
Okay.
So, but what's going to happen over the next few years is we're going to have more and more tools with domain-specific languages, with general-purpose parallel languages, and with RTL like Verilog, and we're going to make mixes of those. So you might have a system where there's lots of soft processors and there's handcrafted perfect data paths for the inner loop of your dot product or whatever. And you'll see stuff like what Microsoft did with Brainwave, where they have custom floating point representations, right? They said, oh, we're able to get the accuracy we want using 8 or 9-bit float. So let's go and build some 8 or 9-bit floating point function units, which presumably they did. So it's a really interesting time. It's a golden age for computer architecture. It's ironically the end of transistor scaling motivates people building custom hardware, because it's the only way to get that next 100x performance leap. And we have new open instruction sets for soft processors like RISC-V, and we have an explosion of different machine learning architectures.
So today all the hype is
All
about...
driven, and we need programming languages and programming models to actually make this accessible to the mainstream developer. Sorry.
Yeah, today at Celsius we have all the hype about ML, but then I think we also see lots of hype about blockchain. Does that impact in some sense what happens on FPGAs as well in order to...
It hasn't hit yet. At a recent FPGA conference, we were remarking at how many machine learning papers, the program is becoming more and more machine learning, as that's the appealing and economically interesting aspect of mapping computations into FPGAs. And we were remarking that there were no blockchain or mining stuff, at least in this academic
maybe
conference. I wouldn't be surprised down the road. I know that it's hard to buy GPU cards at Fry's because of all the Bitcoin mining, etc. And I wonder if down the road it'll be more expensive to buy, or less expensive to buy FPGA time on Amazon F1. If some coin emerges that's economically interesting to accelerate with FPGAs. The curse of FPGAs is historically you build some custom hardware in an FPGA to accelerate a problem, and then you say, oh, now we'll do an ASIC conversion, which saves 10x the area or the power. So FPGAs are great when when it isn't standardized yet, when it isn't rote yet, and you're trying out new algorithms in hardware. Anyway,
so I have a question. So from the peanut gallery.
Yeah.
When I think when you say these things are programmable.
Yeah.
What does that mean in terms of physics, like the physical things that are inside of these programmable units? Like you're moving switches around?
I'll explain. It's fairly straightforward. So all mainstream FPGAs use kind of a programmable gate called a lookup table. And it's just what it sounds like. It's a little Boolean logic table. So for example, if you have what's called a 4-input lookup table, there are 16 one-bit entries in a little memory. And your 4 wires come in, and they of course encode numbers from 0 to 15. So you have 4 signals coming in, and any logic function of those 4 signals can be computed by setting zeros and ones up in that lookup table. And so you can think of a large FPGA as having 1 million 6-input lookup tables. The other part of the technology is the wiring, the programmable interconnect fabric. And you can think of that as little copper wire segments that come out of here, go down here, go over there, and so on. And they're all disconnected. And then you put little, what are called pass transistors or amplifiers at the places where the wires might meet, right? So if I want to route a wire from my output of gate 1 to your input of gate 2, I'll turn some of these connections on, so this segment's connected to this one, which then makes it all the way over to Wolfram. And you can also do fan out, so a single output can go to many places by connecting more wire segments. And then finally, there's a place where the signals come in. There's a bunch of wires passing your front door. Which of them go into your lookup tables? You use what are called multiplexers, which select maybe 1 of 16 wires that go by. So use 4 bits to control which of those wires gets in there. Now, the practitioners don't typically work at this level. They write Verilog, which says my register equals my old register plus 1. And the tool synthesizes that into a net list where there's a 32-bit adder. And there's a tool that reduces that 32-bit adder into a bunch of 6-input logic, lookup table configurations. And then the next layer of the tool says, what physical sites on the chip do I move those 32 little gates into? And then there's another layer of the tool which says, now, how do I program those programmable interconnect points to wire the output of the counter back to the input of the counter? And so there's this, the CAD tools will do this place and route for you, the synthesis place and route. But the number of engineers out there that succeed with both conceiving of the software algorithm and conceiving of the hardware data path and getting the chip to make timing, that is to have its worst delay meet 250 megahertz or 500 megahertz, whatever. There's not a lot of those people in the world, and Microsoft keeps hiring them all and so forth. The industry needs tools that let you write high-level parallel algorithms that then get mapped into this stuff by the clever compiler guy.
Yeah.
And backwards, right?
Yes.
In any kind of compiler tool, there's the back annotation thing where a thing went bad at the lowest level.
Yes.
Why is my register R0, R1 have some funny value in it, and let you map it back up into the, oh, you did a wrong thing in your parallel for loop. Anyway.
Cool. No, that sounds also a lot of fun. Is this exciting times for FPGA and computer?
Well, at the same thing, so a scale bigger than chip is the data center, which is itself like a whole lot of programmable building blocks.
So the funny thing is, so I worked, we both worked for quite some time in computer science. And so initially we learned programming in the small, and I think we understand that meanwhile pretty well. But I don't think that we really understand programming in the large, meaning is programming actually what goes on in the data center and how we in some sense coordinate our processes, how we can monitor and then in some sense debug distributed sessions. So when we worked initially, when we got our education, we worked typically in one programming language. I think there's no reasonable system that's actually only written in one programming language. Everything is in some sense written in many programming languages. And then stitching all those individual parts back together to make meaning out of it is quite a challenge.
It's the same problem at a different scale.
Yes,
coordination. What's the line about, you have a distributed computer when a computer you didn't know exist fails? I can't remember the line.
Leslie Lamport.
Yes.
So a distributed system is a system where a computer goes down, can take down your computer, or a computer you didn't know existed can make your computer useless.
That's right.
Because it went down.
Facebook has hundreds of thousands of machines, and we have probably one of the biggest workloads with, in some sense, our social graph and all that. And so from a programming language point of view, there's, for example, the interesting challenge, how do we actually keep a consistent view? If Charles looks, maybe he's traveling in Europe, he looks at, in some sense, my web page or my Facebook page, and does he actually see what I currently write? Does he see something that I wrote yesterday? If he talks to his partner in the US and asks him, look at Wolfram, what did he write? Does he see something that happens in the US before you see it in Europe? So what's the consistency model? In programming languages, we are all about, we have shared memory, and now what's the consistency? And it's really difficult because if you want to have strong consistency, you get a really slow system. So that's why everybody tries to do with eventual consistency. But we can build lots of caching, and since we then direct, in some sense, your request to the same caches, maybe where I am, so that means since we know each other, we in some sense see each other pretty fast, whereas if you don't know somebody, then that may be going to a very different cache, and therefore there might be more delays, but normally you as a user don't see it. So we play in some sense with the knowledge about our users in order to give each user the best possible notion of consistency.
Right on. And so I'm a node in this. We're all nodes.
Yes, we are all nodes, and so is your photo, and so is in some sense somebody's feed, and we establish then links between in some sense just these different nodes, and we keep track on how recent they are, and we know that if somebody posts a photo, then within the next whatever 24 hours there will be lots of people looking at that photo. But maybe 3 weeks later, nobody's looking at that photo anymore. So in some sense, we are all nodes, but we have a certain kind of hotness, whether we are in some sense popular and recent, and we can play games of where do we store and how do we store this, all the nodes based on access patterns, exactly like keeping things in circle.
Interesting.
So I had a question about scale again. I think scale is fascinating. So the models that we've learned for coordination, for dealing with failure at the one node level, which of them work? Which are you surprised don't work at this scale? And to what extent can we have scale invariant composition mechanisms, so transactions or message passing, which of course work locally, or which work at the full scale, but they start to break down when you try to pretend the failure domains aren't the...
Yeah. So I think it's all cloud providers have in some sense have their data centers. Meanwhile, the networks within the data centers are so fast that you don't have to worry whether it's in some sense the machine in this corner of the data center or in that corner of the data center. So a data center you can view it as has the same latency irrespective of what computer you're talking to. But then you have different data centers, and maybe then different geolocation. Maybe it's all in the US. Okay, you have some sense of latency. Maybe they are worldwide. You have a different sense of latency. And so then question is, so which communications work? So within the data center, since in some sense it's all the same, at data centers, more or less, so you can talk about different failure domains, right? So you can think about that you can organize in some sense all of Facebook's, Amazon's machines in a tree. The leaf of the tree are all the different machines. The root of the tree is, this is in some sense the world. And then you split the trees based on the different locations. Also, there's five data centers in North America and 5 in South America, what have you. And then within the data center, you go down. And so you can now say, so there are different failure domains. If something goes down in one data center, let's see if we use something like Paxos, which gives us in some sense a consistent state that we put the state of the different nodes in different failure domains.
Right.
Then you have failure domains. Now the funny thing is you do not only have the failure domains how you organize in some sense your tree, but you also have failure domains with power, because power might be very different from the failure domain of your network connectivity. So you have actually overlapping failure domains, and what you have to try to see is if you want to build in some sense a failure tolerant system, that you have your replicas then typically in different failure domains, so that you can keep everything in some sense up and running. I think there's lots of trade-off between consistency and what we call eventual consistency, that we don't see that everything is updated all the time. If you use a shopping cart, maybe the product is already being sold, but you still look at something that you can still sell, that you can still buy. Yeah. And so depending then on if it's a financial transaction, then maybe you don't want to deal with eventual consistency. You want to have a consistency that your money is still there. So it's really up to the domain to determine how you deal with the consistency and how you deal with the failure tolerance. But in principle, it turns out that there's not much better than what you had with Paxos in order to get, in some sense, to a consistent state of the world that we are using.
We don't use Paxos locally, because within a machine.
Yeah, we don't. Yes,
that's
okay.
What, sorry, that's what.
Yes.
Yeah.
Yeah. So.
Sense, right.
Yeah.
No,
cool.
It's awesome. Thank you guys.
Thank you.
Maybe we could just keep going, right?
Yes. Maybe another time. Okay.
Definitely.